Hello everyone, this is Shiba, Assistant Professor, Department of Computer Science. Now I am going to give you a lecture on stack organization in digital principles and computer organization. The subject code is 7BCEE2A. In this lecture, we are going to see about what is stack and stack pointer and types of stack, that is register stack and memory stack, and stack pointer in register stack, push and pop operations in register stack, and about memory stack and push and pop operations in memory stack limit and advantage of memory stack. Now let's see about stack. A stack is a storage device that stores information in such a manner that the item stored last is the first item to be retrieved. It is a useful feature that is included in the CPU of most computers is a stack or last in first out. Next, let's see about the stack pointer. Every stack has a stack pointer. The stack pointer always points out the top of the stack. The register that holds the address for the stack is called a stack pointer. Its values always points at the top item of the stack. Now let's see the operations of stack. There are two major operations performed in stack, that are push and pop. Push is an insertion operation. When an item is pushed inside the stack is called as push operation, and when an item is deleted from a stack is called as pop. Here the stack pointer is always point out the top of the item in the stack. There are two types of stack in computer organization. One is register stack and another one is memory stack. Now let's see briefly about register stack and memory stack one by one. Now let's see about register stack briefly. A stack can be placed in a portion of a large memory, or it can be organized as a collection of a finite number of memory words or registers. In the figure we can see that it is the organization of a 64 word register stack. Here the stack pointer register SP contains a binary number whose value is equal to the address of the word that is currently on top of the stack. Here we can see that there are three items are placed in the stack, that are A, B and C in the order of A, B and C. Item C on top of the stack, so that the content of SP, that is stack pointer, is now 3. Now let's see about the push and pop operations in register stack. For the pop operation, to remove the top of the item, the stack is popped by reading the memory word at address 3 and decrementing the content of stack pointer. Item B is now on top of the stack since SP holds address 2. Next, the push operation. To insert a new item, the stack is pushed by incrementing stack pointer and writing a word in the next higher location in the stack. Note here, the item C has been read out but not physically removed here. This does not matter because when the stack is pushed, a new item is written in its place. Now let's see about the stack pointer in register stack. Now let's see about stack pointer in register stack. In a 64 word stack, the stack pointer contains 6 bits because we get the value 64 by multiplying 2 into 6 times. So 2 power 6 will be 64. Since XP has only 6 bits, it cannot exceed a number greater than 63. That is 11111 in binary format. Try to convert 63 into the binary number. We will get 11111 in binary. When 63 is incremented by 1, the result will be 0. Since if we add 1 with 11111, we will get 1. Try to solve. We will get 1000000 in binary. So SP can accommodate only the 6 least significant bits. Similarly, when 00000 is decremented by 1, the result will be 11111. The 1 bit register, full is set to 1 when the stack is full, and the 1 bit register empty is set to 1 when the stack is empty of items. Data register is the register that holds the binary data to be written into or read out of the stack. Initially, SP is cleared to 0, empty is set to 1 and full is cleared to 0, so that stack pointer points to the word at address 0 and the stack is marked empty and not full. If the stack is not full, that is the value of full will be 0. A new item is inserted with the push operation. Now let's see how push operation is done in register stack. Here we can see the implementation of push operation in the form of sequence of micro operations. Here we can see the sequence of micro operations. SP plus 1, it denotes the incrementing the stack pointer. The stack pointer in the first line of execution, the stack pointer is incremented so that it points to the address of the next higher word. A memory write operation inserts the word from data register into the top of the stack in the next line. In the next instruction, note that stack pointer holds the address of the top of the stack and that M of SP, that is denotes the memory word specified by the address presently available in SP. Okay, then the first item is stored in the stack is address 1, the last item is stored at address 0. So here we need to check the conditions. If SP reaches 0, the stack is full of items, so full is set to 1. This condition is reached if the top of item prior to the last push was in location 63 and after incrementing SP, the last item is stored in location 0. Isn't it? Okay. Once an item is stored in location 0, there are no more empty registers in the stack. If an item is written in the stack, obviously the stack cannot be empty. So empty is cleared to 0. A new item is deleted from the stack if the stack is not empty, that is the register empty should be 0. Next, let's see about pop operation in register stack. The sequence of micro operations of pop operation is given here. Let me explain the instruction one by one. The top of the item is read from the stack into data register. That is that denotes the first line denotes that the stack pointer is the decremented. If its value reaches 0, the stack is empty, so the empty register will be set to 1. This condition is reached if the item read was in location 1. Once this item is read out, stack pointer is decremented and reaches the value 0, which is initial value of SP. Note here that if a pop operation reads the item from location 0 and then SP is decremented, SP changes to 11111. Already we have seen that, which is equivalent to the decimal value 63. So in this configuration, the word in address 0 receives the last item in the stack. Note here that an erroneous operation will be the result if the stack is pushed when full value will be 1, when full value is 1, or popped when empty value is 1. Okay. Next, let's see about the memory stack. A stack can exist as a standalone unit or can be implemented in a random access memory attached to a CPU. So the implementation of a stack in the CPU is done by assigning a portion of memory to a stack operation and using a processor register as a stack pointer. So here the figure shows a portion of computer memory that is partitioned into 3 segments. One is program, another one is data, and one more section is stack. Here the program counter PC points at the address of the next instruction to be executed, and the address register points at an array of data. The stack pointer points at the top of the stack. Already we know that no provisions are available for stack limit checks in memory stack. Let's see about push operation in memory stack. In case of adding a new item in memory stack, here I have given 2 lines of micro operations. First line denotes that the stack pointer is decremented so that it points at the address of the next word. In the second line, that denotes that a memory word write operation inserts the word from data register into the top of the stack. Then now let's see the pop operation in memory stack. In case of deleting a new item or an existing item, here I have given 2 lines of micro operations. The top item is read from the stack into data register, that is mentioned in the first instruction. Then the stack pointer is then incremented to point at the next item in the stack. So most computers do not provide hardware to check for stack overflow or underflow. That is the drawback of this system. Now let's see about the stack limit in memory stack. The stack limits can be checked by using 2 processor registers, one to hold the upper limit. In this diagram we can see that the upper limit value is 3000 and the other to hold the lower limit. In this diagram we can see that 4001 is the lower limit. After a push operation, SP is that is stack pointer is compared with the upper limit register, and after a pop operation, stack pointer is compared with the lower limit registers. Next, let's see about the micro operations needed for push and pop operations. The 2 major micro operations needed for either the push or pop operations are an access to memory through stack pointer and updating stack pointer. Which of the 2 micro operations is done first and whether a stack pointer is updated by incrementing or decrementing depends on the organization of the stack. So up to this we have seen about what is stack and stack pointer and operations of stack and types of stack, memory stack, register stack, and push and pop operations in each memory stack and register stack. I hope this lecture is very helpful to you. Thank you all.